In this video, we're going to cover discrete and continuous probability models. And essentially is what I want us to see is how the differences in how we calculate probabilities in each situation. And so let's go ahead and do that. So before we can have that discussion, we need a couple pieces of terminology. So the sample space S of a random phenomenon is the set of all possible outcomes. So if we're just talking about, say, flipping a coin, the only two possible outcomes would be a heads or a tails. And so that would make up the sample space. An event is an outcome or set of outcomes of a random phenomenon. That is, an event is a subset of the sample space. So with the heads or tails example, there's not really very many good examples of events because we just had two outcomes. We had the heads and the tails. So an event would be flipping heads, an event would be getting a tails. We will look at some more complicated events, though, in the next slide. Okay. And then lastly, a probability model is a mathematical description of a random phenomenon consisting of two parts. So we'll have usually like a column that has all the possibilities from the sample space. And then it says in a way of assigning probabilities to events. So below those possibilities or outcomes in the sample space, we'll have the probabilities that go with those. Okay. And specifically right now, I'm really describing how this is going to look when we're looking at a discrete probability model. And I'm doing that because we're going to do that first. In fact, on this next slide here. So here we want to talk about the sample space. If we were to roll a six-sided die like the one pictured here. And so there's only six possible outcomes. We could roll a 1, a 2, a 3, a 4, a 5, or a 6. Okay, so our sample space is just simply the numbers 1 through 6. And I mean the whole numbers 1 through 6. Okay. Some examples of events. So I want to point out that this could just be one thing, like say rolling a 4. Okay. But we could also say things like, what's the probability that we would roll an even number? That would also be considered an event. So an event can be multiple of the outcomes. Okay. And so let's see a couple that I have listed here. So yeah, I'm rolling a 4 and rolling a 3 or less. So that would really mean rolling a 1, a 2, or a 3. Okay. And then lastly, a probability model. Okay. So I was kind of describing this on the last slide. So you can see that top row consists of all the possibilities of what we could roll, all the outcomes, 1 through 6. Okay. Now, this probability model is kind of boring because the probability of rolling a 1 is 1/6, the probability of rolling a 2 is 1/6, and so on. And this is just because each one of these sides is just one side out of 6 sides. And we have an equal likelihood of any of those sides being face up after we roll the die. All right. So this is what it looks like in the discrete case. Okay. And there's a couple things that I want us to note. Okay. If you add up all those 1/6, so if you add up all the probabilities of the events from our sample space, notice that they add up to a certain number. They all add up to 1. Okay. So this is going to be the same case whether we're talking about discrete or continuous. If we were to essentially add up all the probabilities, they should add up to 1. Okay. And so this also brings up another point. If you look at all those probabilities at the bottom of that table, they're all numbers between 0 and 1. Okay. So very often when we're just speaking kind of informally, we'll oftentimes describe probabilities as percentages, but it actually ends up probabilities are technically numbers between 0 and 1. All right, and so we're going to see those kind of things summarized here on the next page. All right, now that we're onto this next slide, I want us to see the things that we were talking about on the previous one. So this first bullet is just saying that any event, its probability has to be a number between 0 and 1. Okay. Similarly, when we're talking about the sample space, if we're trying to find the probability that any event from the sample space occurs, well, it has to be one. It has to be guaranteed to happen. Okay. This is like in the situation with flipping the coin. If we asked ourselves, well, what's the probability of flipping a heads or a tails? Well, the probability is one because it's guaranteed to happen. Okay. And something else that maybe I should mention here, well, then a probability of zero would mean that an event is impossible. Okay. So most of the time, I would say we're not going to see that because if the probability of something is zero, we probably don't want to include it in our sample space. Okay. But there are some situations where will see probabilities of zero. They just probably won't be in our probability model. Okay. All right. So let's go ahead and take a look at our next slide here. Here we go. Okay. So it says finding probabilities. So we're just going to practice finding a few of these. We're actually going to come back to these discrete probability models later, but I want us to finish talking about these discrete models for a moment, and then we'll switch to continuous. Okay. So for discrete here, it says, what is the probability of rolling a one? Okay. Well, we've already established that no matter what number we said, one through six, that probability is going to be 1/6. So I can go ahead and just make that pop up here. And so I've written in here also the notation that we might see. So instead of saying what is the probability of rolling a one, we could similarly write this with this probability notation. We could say P of X equal to one. Okay. Meaning that what's the probability that we roll a one? Okay. Well, and it's 1/6. And then next, what's the probability of not rolling a one? Okay, so there's actually two ways to think about this. We could think about this as, well, not rolling a one would mean that we roll a two, a three, a four, a five, or a six. And so we could add all those probabilities together. Okay. And if we do that, we'll get 5/6. Okay. But another cool way to think about this is all these probabilities need to add up to one. So if the probability of rolling a one is 1/6, then the probability of not rolling a one should be one minus 1/6, which will be 5/6. But you could think about that one either way. And then see what is the probability of rolling a one or a two. Okay. So in this situation, all we need to do is just add those two probabilities. But you can see that every time we compute a probability, we're looking up and finding the corresponding outcomes from this discrete probability model. And then we're working with the corresponding probabilities. Okay. All right. This is going to look a little bit different in the continuous case. Okay. So here's a visual on the right of a continuous probability model. And they usually look like curves. Okay. And so as you can see, this one does look like a curve. Okay. And the total area underneath these curves is one. Okay. Just like when we totaled up all the probabilities in the discrete probability model and they added up to one. When we're talking about probabilities here, we're going to be thinking about them in terms of areas instead of some table. And so, yeah, that total area under the curve is one. But if I were, say, to be asked the question that's kind of posed in that visual, what's the probability that this random variable is between 2 and 4? Well, is what I'd do is I'd find the area under the curve from 2 to 4. Okay. Just like as is pictured here. Okay. Now, this isn't as simple because, right, with the table, we can read those numbers right from it. Okay. Well, it ends up that there's tools on the calculator that can help us find these areas pretty easily. Okay. And that's how we're going to mostly work with continuous probability models. In fact, I would say working with the continuous ones is going to be easier because we're going to be using tools on the calculator to compute all of the probabilities that we're going to do with continuous probability. Okay. All right. So Let's go ahead and go to the next slide here and see an example. Okay. So we have this type of parasitic protozoa, and we're trying to observe how long they are. Okay. And you can see down at the bottom of this visual here that the units are in micrometers. So these are very small. And in fact, you can see they're unicellular parasitic protozoa. So they're very small. Okay. So let's kind of explain what this chart means. But I want you to think about this chart a lot like we thought about our empirical rule. Okay. So is what it's saying is that 1% of these protozoa are smaller than 15 micrometers. And so I'm going from left to right here at the moment. And then 34% of these protozoa are between 15 and 20 micrometers. Then 20 to 25, we have that blank. We'll figure out what that is. That's going to be part A for us. And then from 25 to 30, 21% of protozoa have those lengths. And then lastly, 3% of these protozoas will have a length of 30 or more micrometers. Okay. And notice I said it in terms of percentages because that's how we're actually used to thinking about probability outside of mathematics. Okay. But in actuality, you can see that on the chart, all those numbers are between 0 and 1, as they should be. Now, to do part A, find the probability that a randomly chosen of this type of protozoa have a length between 20 and 25 micrometers. Well, I just need to know that the total area under this curve is 1. Okay. So if I do 1 minus the rest of the area, I should be able to find the area that I'm trying to find. Okay. And that's exactly what I'm going to do here. I've just done 1 minus the other 4 areas, and that should leave me with the area of the piece I'm left with. Okay. And so that does make me want to say one more thing here, which is we've kind of already said it, but those numbers there, as I was saying that, we want these to be decimal numbers when we're talking about probabilities. But I also really want to emphasize that say 0.21 that you're seeing there between 25 and 30, it means multiple things. Okay. So for one, it tells us that the area under the curve from 25 to 30 is 0.21 units. Okay. Now, that's an important thing to know. And the other thing that we've been talking about is also important to know, which this also means that, again, about 21% of this type of protozoa have lengths between 25 and 30 micrometers. Right. Well, then part B here, find the probability that x is equal to 2. So we want to know, well, what's the probability that a protozoa is equal to, or its length is exactly 25 micrometers. Okay. So here's the deal. Okay. Just discrete probability models are designed to answer questions like this one in part B. Okay. Continuous probability models are not meant to answer questions like B. Okay. I want to explain why. Okay. So just a second ago, we were talking about how the area under the curve from 25 to 30 is 0.21 square units. Okay. Well, to find an area, and let's just imagine a rectangular area for a second, you need both a length and a width. Okay. Well, if I were to take this image here and go to 25 and just draw a line, okay, just draw a line there, we'd have this line whose height goes from the x-axis up to the curve. But then what's the width of that line? Okay. And the answer is, well, then the width of a line is 0. Okay. So the area of that section is 0. Okay. And so the probability we get here is 0. Okay. And I don't want you to think about this as this is the probability of this event happening. I want you to think about this as we're just not meant to answer these types of questions with continuous probability models. Okay. But here's another way to think about this. When we talk about these heights here, okay, let's just pretend for a second that the smallest one of these protozoas ever seen was 10 micrometers, and the largest being, say, 35 micrometers. Okay. If that were the case, okay, then you would expect that if we went to measure these protozoa, they're not necessarily going to end up with nice whole number lengths in micrometers. Okay. So again, one of these protozoa might be 25.6354 micrometers in length, something crazy like that. Okay. Well, so if that's the case here, okay, then that means in between 10 and 35, there are an infinite number of possible lengths that these protozoa could be. Okay. So we'd be taking our one option, which is 25, out of an infinite number of options. Okay. And you might remember if you take a number like, say, 1 and you divide it by a really big number, you get a really small number. Okay. And we're kind of talking about dividing by infinity here in some sense. And so you could imagine here that that would lead us to concluding that this probability is 0. Okay. Now, the remaining two probabilities we're going to do are ones that we might be asked. Okay. Again, part B, it doesn't really make sense to ask that type of question. Okay. All right. Now, C, you can see looks just like A, but it's missing the equals to's. Okay. And the whole point in this is to point out that including 20 and 25 in the continuous case or excluding them makes no difference because those are just single points. Okay. And single points have an area of 0. So we have, whether we include them or exclude them, we're either adding in an area of 0 or subtracting an area of 0, which makes no difference. So this answer to C should be exactly the same as part A. Okay. This will not be the case when talking about discrete probability models. Okay. But luckily with continuous, you can kind of ignore whether it says equal to or not on the inequalities. Okay. And then lastly, what's the probability that x is less than 25? So we just want to add up all the areas that are to the left of 25 micrometers. Okay. So the first one in between 20 and 25, we just found that that was 0.41. Okay. And then the area from 15 to 20 is 0.34. And then the area from 15 and below is 0.01. So I just need to add those together. Let me do that. There we go. There's part B, where you can see we're adding those three areas together and getting this 0.76. So let's go ahead and move on to our next slide. So we have the normal distribution is a continuous probability model. I've kind of already hinted at this when we were working on the last example, but you can see I've taken our empirical rule, and instead of having the percentages in there, I have the proportions or the decimal form of those percentages. Okay. And so is what this means is the area under the curve that is within one standard deviation of the mean has an area of 0.68. The area under the curve then that is within two standard deviations of the mean will have an area of 0.95. And then lastly, the area under the curve that's within three standard deviations of the mean will contain point or its area will be 0.997. I almost went back to talking about percentages there. It's really easy to switch back and forth here. In this slide, we are going to look at an example of our empirical rule, but this time we're going to use the probabilities as opposed to the percentages. And bar-headed geese cross the Himalayan mountain range during their biannual migration, which means that their physiology and flight must adapt to very high altitudes, greater than 3 miles. Okay. Which means that there's going to be a low air density, and that means it's going to be harder for them to fly. Okay. And researchers implanted small recording instruments on wild bar-headed geese and found that the mean wing beat frequency uh, was 4.25 flaps per second, which flaps per second, we could call that unit, we could call it hertz. And the standard deviation was zero point 0.2 hertz, or zero point 0.2 flaps per second. And so this says to sketch the density curve. So is what I'd want you to really do here is make a picture of a bell-shaped curve. Okay, so something that looks normally distributed. And then I'd want you to put in vertical lines for the mean, and for 1 standard deviation from the mean, 2 standard deviations from the mean, and 3 standard deviations from the mean. And then is what we could do from there is we could put 4.25 in the middle, our mean, and we could add zero point 0.2 repeatedly to get the um, to get the labeling for the 3 vertical lines to the right, and we could subtract 0.2 from 4.25 repeatedly to get the labeling for the 3 vertical lines to the left. And to be a little bit more clear, this is what I mean right here. Okay. And so again, notice I do not have the percentages here. I have the probabilities, or the areas. And so, is what we're going to do on the next slide. We'll just answer a question about this normal distribution. Okay. So it says, find the probability that a randomly selected bar-headed goose flying over the Himalayan mountain range would have a wing beat frequency of 4.45 flaps per second or more. So we just need to find 4.45 flaps on the x-axis over there in our normal distribution, and I can see that that is 1 standard deviation above the mean. And so I want to add up those 3 areas to the right of 4.45. Okay. And if I do that, okay, I get 0.16. Okay. And so if this were earlier in the quarter, instead of talking about the probability, we would have said that there was a 16% chance that a randomly selected bar-headed goose would have a wing beat frequency of 4.45 flaps per second or more. And now instead is what we might say is the probability that a randomly selected bar-headed goose flying over the Himalayan mountain range would have a wing beat frequency of 4.45 flaps per second or more is 0.16. Right. So that actually does wrap up this part here of kind of distinguishing discrete probability models versus continuous. Okay. But I want to bring up one last thing, which is that there was a limitation to our empirical rule, and that was we had to always be a whole number of standard deviations from the mean. Okay. And so, is what we're going to see in our next video is that there is a way on the calculator that we can find these probabilities really easily. And that's precisely what we're going to do. Okay. And it's going to end up that the normal distribution we're going to work with for all this week and all of next week. It's going to be a really important tool. All right. And so that is it for this video.